Welcome back to the next video, everybody. Today's video will be on prolongations. So we're going to start pushing towards Raynaud's results that we're going to use in the proof of Fermat's last theorem. So the setup is this. First of all, I'll just refer you to Raynaud's type PPP paper, I call it, which I'll call RSG from here on out, for just additional details throughout the rest of this entire chapter, chapter 5 of my notes. Okay, so let's set up prolongation. For simplicity, we'll assume that our ground ring R is a DVR with mixed characteristics. So what I mean is the characteristic of the ring is 0, but the residue characteristic of the residue field is a prime P, let's say. We'll give R a field of fractions K and a uniformizer pi. We'll call the residue field lowercase k, and that's just R mod pi R. We'll call the characteristic of the residue field P, and we'll call the normalized evaluation V. Okay, so that's with respect to the uniformizer pi. And we'll let E equals V of P be what we call the absolute ramification index. So that's just whatever the valuation of P is. We'll just call that E. So what's a prolongation? Well, let's let G0 equals spec of A0 be a finite commutative K group scheme. So we're a group scheme over the field of fractions of a DVR here, and we'll call that K. A prolongation of G0 to spec R, so I want to somehow kind of bump up G0 from a K group scheme to an R group scheme in some sense. What is this? This is a finite flat R group scheme G, whose generic fiber is G0, the given scheme. So the generic fiber, remember, is just the fiber product with the generic point. So you're sort of allowing denominators in and looking at what happens to the scheme, essentially, okay? Or if you like, it's not really that you're allowing arbitrary denominators in. A better way of thinking about it is by moving to the generic fiber, you're sort of looking at what happens at all but finitely many primes P, if you like. Okay. Okay, so that's what a prolongation is. The isomorphism classes of prolongations of a given G0 are represented by R group schemes G of the form G equals spec A. So we get other affine schemes here. And what is A? Like, how do you characterize the A's, right? So A is a finite R subalgebra of A0, the given ring that contains R and spans A0, but you also want to make sure that C of A is contained in A tensor A over R. And what is C here? It's the co-multiplication map in A0. So it's the co-multiplication map from A0 to A0 tensor A0 over R. Okay. So how about Cartier duals of prolongations? Okay, so we'll let GD0 be spec of AD0, and that'll be the Cartier dual of G0. And we'll let bracket from A0 to AD0 to K be the canonical duality bilinear map from last video. So what's the Cartier dual of a prolongation then? Well, let's call the prolongation G equals spec A, and we'll call the Cartier dual GD, and it'll be spec of AD. And the real key is here is, what is this AD actually? How do you recognize the Cartier dual of a prolongation? Well, AD in AD0 is called a complementary module to A. The complementary module to A. It's the set of all lambda in AD0 such that bracket lambda F is in R for all F and A. In other words, it's just the R module maps from A to R, right? That's what AD is. I mean, that's sort of what you expect it to be, right? If this is supposed to be a dual. Now, the multiplication on the kind of the dual ring here. So the multiplication on AD0 tensor AD0 to AD0, that's just the transpose of the co-multiplication C from before. And so this condition that popped up earlier, this C condition here, the condition that C of A is an A tensor A over R, what's that equivalent to? Well, it should be equivalent to the condition that AD is in AD. And the upshot of all this is actually pretty nice. It says that a finite R submodule A of A0 that contains R and spans A0 is the ring of a prolongation if and only if both A and AD are closed under multiplication. So if and only if both A and its complementary module are closed under multiplication, if you want to make it sound even nicer. Okay, so we can actually detect whether or not kind of, submodules of A0 are actually rings of prolongations pretty easily, and that's pretty nice. Okay, so here's kind of one of the key results that we're going to need going into the next videos. You can put a partial order on the set of prolongations of G0. How do you do that? It's pretty easy. Just let G equals spec A and G prime equals spec A prime be two prolongations of G0, and we'll write G is bigger than or equal to G prime if A contains A prime. Or if you like, using categorical equivalence, if there's a morphism from G to G prime, which must be unique, inducing the identity on G0. And you can prove pretty quickly using Cartier duality that the following must be true. Proposition 5, if G0 has a prolongation, it must have a maximal prolongation G plus and a minimal prolongation G minus with respect to this partial order. And this is proven on page 146 of CSS. So we'll start using this to push towards the two main results of the chapter that we need for Fermat's last theorem, the theorems of Raynaud. And so we'll start that tomorrow, and I'll see you then. Thanks for watching.